The most relaxing facts about lightning. To fall asleep. To right now, as you settle into this moment, lightning is striking Earth 50 times every second. 50 brilliant bolts painting the sky somewhere on this planet. And here is something even more remarkable. Your body creates its own tiny lightning with every heartbeat, every thought traveling through your nerves. You are electric. This is a place for calm curiosity, where we explore the gentle science of our world. So find your most comfortable position and let us begin. Tonight, we explore lightning, not the loud, scary thing from childhood storms. The real lightning, the physics and beauty of it, what it actually is when you strip away the drama and look at the pure science underneath. Lightning is electricity. That is the simple truth. It is the same force that powers your phone, runs through the wires in your walls, makes your muscles move when you decide to lift your hand. But lightning happens in the open air, a river of electrons jumping from cloud to ground, or cloud to cloud, following a path of least resistance through the sky. Each bolt carries about 1 billion volts. That number is hard to picture. So let me give you something concrete. A lightning bolt is 5 times hotter than the surface of the sun. 5 times. The sun's surface runs about 10,000 degrees Fahrenheit. Lightning reaches 50,000 degrees. All that heat concentrated in a channel narrower than your thumb. That is what creates the light we see. When electricity surges through air at that temperature, the air itself glows white hot. The molecules of nitrogen and oxygen get so energized they emit light. Pure, brilliant light that travels to your eyes faster than you can blink. The whole bolt lights up for less than a second, but in that flash, you are seeing air turned into plasma, the fourth state of matter, beyond solid, liquid, and gas. The colors tell us secrets. Most lightning looks white or yellow because we are seeing that superheated channel at its hottest. But sometimes you see blue or purple. That happens when you are looking through rain or hail. The water filters the light, changes what reaches your eyes. Red lightning is rarer. It means you are seeing the bolt through heavy rain or through a lot of atmosphere, like at sunset when the sky looks orange for the same reason. If this kind of gentle science brings you calm, consider subscribing. You will join thousands of others who love these quiet journeys through the facts of our world. And if you are listening from somewhere far away or somewhere close, leave a comment. Tell us where you are and what time it is there. It helps us feel connected, all of us scattered across the planet, all looking up at the same sky where lightning writes its temporary messages. Pink lightning exists too. It happens when there is a lot of moisture in the air, mixing with dust or pollution. Orange lightning means there is dust in the atmosphere, common in desert regions where dry storms kick up sand. Green lightning is the rarest, usually seen during volcanic eruptions or severe storms, created when lightning interacts with certain particles in the air. Every color is the same phenomenon: electrons flowing, air heating, light emerging, just filtered through different conditions, different atmospheric cocktails that change what makes it to your eyes. The bolt itself moves at about 220,000 miles per hour. That is 1/3 the speed of light, fast enough to circle Earth 9 times in the span of a single second. All that speed, all that heat, all that energy, packed into a moment so brief, it is essentially instantaneous to our slow human perception. But here is the question that makes you lean forward that makes this more than just facts about electricity. Where does this incredible light come from? What builds up all that energy in the first place? The answer lives in the clouds themselves, in a process so elegant it feels like magic, even when you understand the physics. And that is where we go next. Inside every thunderstorm, tiny pieces of ice are colliding. Billions of them, crystals smaller than snowflakes, bumping into each other in the dark turbulence of the cloud. And with every collision, something invisible happens. Electricity is born. Here is how it works. When ice crystals bump together, electrons get scraped off. Electrons are the smallest units of electrical charge, the particles that make up electricity itself. They live on the outer shell of atoms, loosely held, easy to knock free. So, when two ice crystals collide in a cloud, some electrons transfer from one to the other. The smaller, lighter crystals lose electrons. They become positively charged. The wind carries them up to the top of the cloud because they weigh almost nothing. Meanwhile, the larger, heavier crystals gain electrons. They become negatively charged. Gravity pulls them down toward the bottom of the cloud. This is friction at work. The same force you feel when you rub a balloon on your hair and it sticks to the wall. The same principle that makes static shock when you touch a doorknob in winter. Except this is happening at enormous scale, with billions of particles, building charge powerful enough to leap miles through air. The cloud becomes a battery, positive charge collecting at the top, negative charge pooling at the bottom. And like any battery, it wants to balance itself. It wants those charges to reunite. But air is a good insulator. It resists the flow of electricity. So the charge just keeps building, and building, and building. For this to work, the storm needs to be tall, really tall, at least 20,000 feet from base to top, often much more, because you need different temperature zones inside the same cloud. The top needs to be cold enough for ice, below -15 degrees Celsius. The middle needs updrafts strong enough to carry those light crystals upward against gravity. The bottom needs to be warm enough that some liquid water still exists. It is a factory with very specific requirements. You need water vapor condensing into droplets. You need those droplets freezing into ice. You need powerful updrafts, sometimes moving at 60 miles per hour straight up. You need the right temperature gradient from bottom to top. Take away any of these ingredients and the battery does not form. The taller the storm, the more charge it can separate. Some supercell thunderstorms reach heights of 50,000 feet or more. Imagine a building 10 miles high, filled with colliding ice crystals, all of them contributing their tiny bit of charge to the growing electrical field. Each individual collision creates almost no voltage, but billions of them happening simultaneously, constantly, for minutes or hours, add up to something incredible. Meanwhile, the ground below the cloud responds. The negative charge at the cloud base pushes electrons in the Earth downward. This leaves the surface with a positive charge, especially on tall objects. Trees, buildings, towers, even blades of grass. All of them develop a positive charge on their tips, reaching up toward that negative cloud base, like the ground is trying to complete a circuit. The voltage difference grows. 1 million volts, 10 million, 100 million. The air between cloud and ground is being stressed, pushed to its breaking point. Air normally insulates well, but every material has a limit. For air, That limit is about 3 million volts per meter. Once the voltage difference exceeds that threshold across enough distance, the air itself breaks down. It stops being an insulator. It becomes a conductor. And that is when the invisible ladder begins building downward. When the lightning actually starts to form, step by careful step, reaching down from cloud to earth in a process most people never see because it happens in darkness, too dim for human eyes. That is where we go next, to the moment before the flash, to the invisible descent that sets up everything. The lightning starts in darkness, complete darkness. No flash yet, no light at all, just an invisible finger of electricity reaching down from the cloud, feeling its way toward Earth. This is called the stepped leader. It moves in jumps. Each jump covers about 50 meters, roughly half the length of a football field. It pauses for 50 microseconds, then jumps again. Pause, jump, pause, jump, building a conductive path through air, one segment at a time. Why does it step instead of flowing smoothly? Because air resists. Even though the voltage has broken down the air's insulating properties, the process still takes work. Each step ionizes the air ahead of it, ripping electrons off nitrogen and oxygen molecules, creating a channel of plasma. That takes time, microseconds. Then, the leader extends through that newly conductive section and starts working on the next. You cannot see this happening. The stepped leader emits almost no visible light. It glows very dimly, maybe 100 times fainter than the final lightning bolt. Your eyes would register it as basically nothing, just darkness, with maybe the faintest purple hint if you were looking right at it, which you would never be because you would not know where to look. It moves fast despite the stepping. The leader descends at about 60,000 miles per second. That is 1/3 the speed of light. In the time it takes you to blink once, the stepped leader could travel from cloud to ground dozens of times over. The entire descent, even in a tall storm with several miles to cover, takes less than 20 milliseconds, 20 thousandths of a second. The path is not straight. It zigzags, it branches. It looks like a river delta turned upside down, or the roots of a tree. This happens because air is not uniform. Some regions have slightly more moisture, or dust, or ions from previous lightning. These areas conduct better. The stepped leader takes the path of least resistance, probing in multiple directions at once, following whatever route is easiest. Each branch competes to be the main channel. Most of them fail. They dead end partway down. But one branch keeps winning, keeps finding the easiest path forward, extends farther than the others. That winning branch becomes the primary channel, the route the main discharge will eventually follow. As the leader gets closer to ground, something else begins happening. The positive charge on the Earth's surface responds more strongly. It concentrates on tall objects. A positive streamer, a small discharge, starts reaching upward from whatever object is tallest in the area. A tree tip, a building corner, a radio tower, sometimes just a rock on a hilltop. The positive streamer only extends a few dozen meters up. It is tiny compared to the stepped leader descending from miles above. But it is there, reaching, and the stepped leader is feeling its way down, branching, testing different paths, getting closer with each jump. The voltage gradient between them intensifies. The electric field in the gap grows stronger. The air between them becomes more and more stressed, more ionized, more ready to conduct. Both paths are probing toward each other now, one invisible finger reaching down, one invisible finger reaching up, the gap between them shrinking. 50 meters, 30 meters, 10 meters, and then they touch. The circuit completes. The conductive path exists, an unbroken channel from cloud base all the way to ground. And in that instant, everything changes. Because now, the real lightning can happen. The flash you actually see. The return stroke that shoots back up the channel at a third the speed of light, carrying all that stored energy in one brilliant, explosive surge. That moment of connection is where the real magic lives. Contact. The stepped leader touches the upward streamer. The circuit closes. And everything that has been building in the cloud, all that separated charge, all those billions of colliding ice crystals worth of electrical potential, suddenly has a path to ground. The electrons rush downward. But what you see, what creates that brilliant flash, is actually moving upward. This is the return stroke. It races from ground back up to cloud at 100 million miles per hour, 1/3 the speed of light, following the exact path the stepped leader carved out, but in reverse and carrying 1,000 times more current. Think of it like this. The stepped leader built a hallway through the air, a conductive channel, but it was dim, tentative, just ionized enough to barely conduct. The return stroke is a flood of electrons pouring through that hallway all at once. And when that much current flows through air that fast, the air lights up like a filament in a light bulb. Except this filament is miles long and hotter than the surface of the sun. The current peaks at about 30,000 amperes. For comparison, a typical house electrical circuit handles 15 amperes. A car battery might deliver a few hundred when starting your engine. 30,000 amperes is enough to power a small town. All of it concentrated in a channel narrower than your finger. All of it flowing in less than a millisecond. That incredible current density creates the temperature, 50,000 degrees Fahrenheit in the core of the channel. The air molecules do not just get hot, they get ripped apart. Nitrogen splits into individual atoms. Oxygen does the same. Electrons get stripped away completely. What remains is plasma, the fourth state of matter, glowing white hot. This is what you see when you see lightning. Not the stepped leader creeping down, not the charge separation happening in the cloud. The return stroke, the upward surge, the moment all that potential energy converts to light and heat and sound in one explosive release. The light moves outward from the channel at the speed of light. It reaches your eyes in microseconds if you are close, milliseconds if you are far away. Your brain registers white or yellow or blue, depending on what the light passes through on its way to you. Clear air gives you white. Rain gives you shades of blue. Distance gives you yellow or orange. But the return stroke is not alone. Often, there are multiple strokes using the same channel. The first return stroke clears the path. Then, more charge flows down from the cloud in what is called a dart leader. It moves faster than the stepped leader did, because the channel is already ionized, already warm, already conductive. The dart leader reaches ground and triggers another return stroke. Flash, then maybe another. Flash, flash. This happens so fast, your eyes cannot separate the individual strokes. You see one continuous flicker instead of distinct pulses. But if you filmed lightning with a high-speed camera, you would see it. 3 or 4 or sometimes a dozen separate return strokes, each using the same channel, each adding its own surge of light. The whole sequence lasts maybe half a second. All those strokes, all that energy, compressed into a moment that feels instantaneous. A single bolt transfers about 1 billion joules of energy. That is enough to power a 100-watt light bulb for about 3 months. Except it all gets released in a fraction of a second instead of spread across 90 days. The power level, the rate of energy transfer, is what makes lightning so spectacular. Not the total energy, but how fast it happens. And all of that energy, all of that heat, all of that light leaves traces behind, changes the air itself, creates molecules that were not there before, splits atoms and recombines them in new ways. That is where we go next, to the chemistry of what lightning creates. That surge of energy creates more than light. It creates sound, thunder, the voice of lightning itself, rolling across the sky, seconds after the flash fades. Here is what makes that sound. The lightning channel heats the air to 50,000 degrees in microseconds. The air expands, violently, faster than the speed of sound. This creates a shockwave, like a sonic boom from a jet, except it comes from a channel miles long instead of a single aircraft. The air expands so fast, it compresses the air around it into a pressure wave. That wave moves outward at the speed of sound, about 760 miles per hour at sea level. This is thunder, not some separate phenomenon, just the sound of air being explosively heated and then rapidly cooling. The crack you hear from close lightning is the shock wave hitting you nearly undistorted. A sharp, violent sound because you are hearing it almost immediately, before the sound waves have time to spread out and reflect off anything. It is pure acoustic energy, unfiltered, but thunder from distant lightning rumbles. It rolls. Why? Because the sound waves take different paths to reach you. Some travel directly through the air. Others bounce off the ground, off buildings, off hills and valleys. Each reflected wave arrives at a slightly different time. Your ear receives dozens or hundreds of overlapping sound waves, all from the same lightning bolt, but all taking different routes and arriving out of sync. The lightning channel itself contributes to the rumble. A bolt might be 3 miles long, stretching from cloud to ground. The sound from the bottom reaches you first. The sound from the top takes longer because it has farther to travel. So, you hear one continuous roll instead of a single clap, because you are hearing sound from different parts of the same bolt arriving in sequence. Temperature affects how sound travels. Cold air carries sound differently than warm air. Wind bends sound waves. Humidity changes how fast sound moves. All of these factors shape what you hear. Two people standing a mile apart during the same storm will hear different thunder because the air between them and the lightning is different. You can measure your distance from lightning using thunder. Count the seconds between the flash and the sound. Every 5 seconds equals about 1 mile. This works because light travels so much faster than sound that the light reaches you essentially instantly, while sound crawls along at 760 miles per hour. The gap between seeing and hearing tells you how far away the bolt struck. Close lightning within a quarter mile produces thunder that hurts. The pressure wave is strong enough to rattle windows, set off car alarms, make your chest vibrate. Some people report feeling the thunder more than hearing it when lightning strikes very close. The shockwave hits you physically. Distant lightning might be completely silent, not because it did not make sound, but because the sound dissipated before reaching you. Thunder rarely travels more than 10 miles. The sound waves spread out. lose energy, get absorbed by the air and ground. Beyond 10 miles, even a powerful bolt produces thunder, too faint to hear over ambient noise. Inside the lightning channel itself, the sound would be deafening if you could somehow survive there. Estimates put it at around 120 decibels at the source, louder than a rock concert, loud enough to cause immediate hearing damage. The thunder you hear a mile away is already diminished, already scattered and softened by distance. But thunder carries more than just noise. It carries information. The timing tells you distance. The pitch tells you how hot the channel was. The duration tells you how long the bolt was. Every rumble is a message about the physics that created it, written in sound waves, delivered to your ears at the speed of sound. And lightning itself leaves other messages too, written in the ground, written in the chemistry of the air, changes that last long after the thunder fades. Lightning does not just pass through air, it changes air, rearranges it at the molecular level, creates new substances that were not there before the bolt struck. Start with nitrogen. It makes up 78% of the air you breathe. Normally, nitrogen exists as N2, two nitrogen atoms bonded tightly together. This bond is strong. It takes tremendous energy to break it. Lightning has that energy. When the bolt heats air to 50,000 degrees, nitrogen molecules split apart. The two atoms separate. Free nitrogen atoms, highly reactive, desperate to bond with something. And there is plenty of oxygen nearby, making up another 21% of the air. The nitrogen grabs oxygen atoms, forms nitrogen oxides. No, NO2, other combinations. These nitrogen oxides dissolve in water. They fall with the rain. They soak into soil. And here is the remarkable part. Plants need nitrogen to grow. Their leaves, their stems, their roots, all built from proteins that require nitrogen. But most plants cannot use nitrogen gas from the air directly. The N2 bond is too strong for them to break. They need it in a form they can absorb through their roots. They need it fixed, combined with other elements. Lightning does this. It fixes nitrogen, makes it bioavailable. Every bolt that strikes near farmland or forest delivers usable nitrogen to the soil below. Ancient lightning essentially fertilized early Earth, providing the nitrogen compounds that early life needed to develop proteins and DNA. Before life invented its own nitrogen-fixing bacteria, lightning was the primary source. Even now, with all our modern agriculture and synthetic fertilizers, lightning still fixes about 8 million tons of nitrogen every year. Free fertilizer made by electricity, falling from the sky in every thunderstorm. That is roughly 10% of the nitrogen plants need globally. Not a trivial amount, a substantial contribution to the nitrogen cycle that supports all plant life on Earth. But lightning creates something else too. Ozone. You know this molecule. O3, 3 oxygen atoms bonded together. Normal oxygen is O2, 2 atoms. Lightning's energy rips oxygen molecules apart and lets them recombine in new ways. Some form O3, ozone. This is what you smell after a thunderstorm. That fresh, clean, slightly sharp scent. Not rain on concrete, not wet earth. That is called petrichor, and it comes from bacteria releasing compounds when rain hits dry soil. The smell we are talking about is different, sharper, electrical. That is ozone. Your nose is remarkably sensitive to it. You can detect ozone at concentrations as low as 10 parts per billion. Most substances require thousands or millions of parts per billion before you notice them. But ozone, your nose finds it instantly. A few molecules in every billion, and you register that distinct after-storm smell. Ozone is unstable. Those 3 oxygen atoms do not stay bonded for long. Within hours or days, ozone breaks down back into regular O2. But while it exists, it is reactive. It oxidizes things, purifies air by breaking down pollutants and odor molecules. This is why the air smells cleaner after storms. Not just because rain washed away dust, because lightning created ozone that is actively cleaning the air at a chemical level. Up in the stratosphere, ozone forms a protective layer that blocks ultraviolet radiation. But near ground level, the ozone from lightning is temporary, a brief chemical gift that scrubs the air and then vanishes. Every thunderstorm creates it. Every bolt contributes its small amount. The energy also creates other molecules, hydrogen peroxide, various hydroxyl radicals, all short-lived, all reactive. The air after a lightning strike is chemically different than the air before, enriched with compounds that would not form without that electrical surge. And lightning changes more than just the air. It writes its signature in the ground itself, creates permanent records of its passage, freezes its energy into forms that last for millions of years. That is where we look next, at the physical traces lightning leaves behind. Lightning is older than life itself. It was striking Earth 4 billion years ago, when the planet was young and empty. No plants, no animals, no bacteria, just rock and water and a thick atmosphere of methane, ammonia, carbon dioxide, nitrogen, and lightning. Those early bolts did something extraordinary. They took simple molecules and made them complex, broke them apart, and reassembled them into the building blocks of life. In 1952, a scientist named Stanley Miller recreated this process in a laboratory. He put water, methane, ammonia, and hydrogen in a flask, added electrical sparks to simulate lightning, waited. After a week, the water had turned brown. He analyzed it and found amino acids, the fundamental components of proteins. Lightning had created them from basic atmospheric gases. This probably happened on early Earth. Billions of lightning bolts over millions of years, each one creating a tiny amount of organic molecules. Those molecules accumulated in the oceans, combined in new ways, eventually became complex enough to self-replicate. Life began, and lightning may have written the first chapter of that story. Even after life established itself, lightning remained essential. We talked about nitrogen fixation, 8 million tons per year. But consider what that means for ecosystems. In tropical rainforests, where thunderstorms happen almost daily, lightning delivers a constant supply of usable nitrogen to the soil. The forest depends on it. Remove lightning from the equation, and many ecosystems would be nitrogen-starved. Grasslands benefit too. The African savanna experiences thousands of thunderstorms each year. Each storm fixes nitrogen. Each bolt adds to the soil's fertility. This supports the grasses. The grasses support the grazers. The grazers support the predators. Lightning sits at the foundation of the food chain, invisible but crucial. In the ocean, lightning's nitrogen compounds wash from land into rivers and eventually into the sea. There, they feed phytoplankton, microscopic plants that form the base of marine food webs. These phytoplankton produce half the oxygen in Earth's atmosphere. You breathe oxygen made by plants that were fertilized by nitrogen that was fixed by lightning. The connection is direct. Forest fires started by lightning play a role too. Before humans suppressed fires, Lightning ignited thousands of blazes every year. These fires cleared old growth, returned nutrients to soil, created mosaics of different habitats. Many ecosystems evolved with fire as a regular feature. Some pine cones only open and release seeds after exposure to fire. Lightning shaped entire forest structures. The fires also released nutrients locked in dead wood. A fallen tree might take decades to decompose naturally. Lightning-sparked fire releases those nutrients in hours. Ash fertilizes the soil. New growth springs up quickly. The forest regenerates faster than it would without fire. Beyond Earth, scientists think lightning may have played a similar role on other planets. Titan, Saturn's largest moon, has a thick atmosphere and probably has lightning in its methane clouds. Could those bolts be creating complex organic molecules the same way Earth's early lightning did? Venus almost certainly has lightning in its sulfuric acid clouds. Mars might have had lightning when it still had a thick atmosphere billions of years ago. Lightning is a universal process. Anywhere you have an atmosphere and storms, you probably have lightning. And wherever lightning strikes, it changes chemistry, creates complexity from simplicity, takes basic molecules and builds them into more interesting forms. On Earth, this has been happening for 4 billion years. Every storm adds its small contribution. Every bolt fixes a little nitrogen, creates a few organic molecules, sparks, an occasional fire. These effects accumulate. Over geological time, they shape the planet's chemistry and biology in profound ways. But lightning's power reaches beyond chemistry and life. It writes itself into the physical structure of Earth itself, leaves marks that last millions of years. When lightning strikes sand, it creates glass, instant glass, formed in the fraction of a second that the bolt touches ground. These glass formations are called fulgurites, from the Latin word for lightning. They are frozen electricity, lightning turned solid. Here is how it happens. The bolt carries enough current to heat the sand to over 3,000 degrees Fahrenheit. Sand is mostly silicon dioxide, the same substance glass is made from. When silicon dioxide gets hot enough, it melts. The lightning channel, narrower than a pencil, melts the sand in a tube shape, following the exact path the electricity took through the ground. The process is nearly instantaneous. The sand melts and then cools within seconds. It fuses into glass while still holding the shape of the lightning's path. The result is a hollow tube of glass, rough and bubbly on the outside, smoother inside, branching and twisting through the sand like a root system made of lightning. Most fulgurites are small, a foot or two long, maybe an inch in diameter, but some are massive. The longest ever found measured nearly 17 feet. It branched multiple times, creating a complex network of glass tubes, all radiating from a single strike point. Imagine lightning reaching that deep into the earth, melting sand all the way down, leaving this permanent record of its passage. The glass itself is unique. Regular glass is made slowly, heated and cooled in controlled conditions. Fulgurite glass forms in milliseconds under extreme heat. This creates a different structure. More bubbles, more impurities. Sand grains partially melted and fused together, rather than completely uniform glass. Each fulgurite contains tiny pockets of the original sand, bits of rock, sometimes even metal particles from minerals that were present when the lightning struck. You can find fulgurites in deserts, on beaches, anywhere there is sandy soil and thunderstorms. the Sahara Desert has them, the beaches of Florida, the sand dunes of the Great Plains. They are rare because they are fragile. The glass is brittle, easily broken. Most fulgurites shatter soon after forming, destroyed by shifting sand or weather. The ones that survive long enough to be found are lucky accidents of preservation. Scientists study fulgurites to learn about ancient lightning. A fulgurite from 1 million years ago tells us that lightning struck that exact spot, that the sand was there, that the climate supported thunderstorms. They are time capsules. Each one preserves information about temperature, mineral content, even the magnetic field at the moment of the strike, because the intense heat can magnetize iron particles in the sand. The shape tells us about the lightning itself. Straight fulgurites mean the bolt went directly into flat ground. Branching ones mean the lightning split as it traveled through layers of different resistance. Thick fulgurites suggest powerful bolts with high current. Thin ones indicate weaker strikes. Some fulgurites contain organic material. A lightning strike near vegetation might melt sand that contains plant matter. The carbon from those plants gets trapped in the glass, preserved for potentially millions of years. You could, in theory, find a fulgurite containing traces of grass from the Pleistocene era, locked in glass created by one bolt on one afternoon 2 million years ago. People collect fulgurites. They are sold as curiosities, as jewelry sometimes. A necklace made from a piece of fulgurite is literally wearing frozen lightning, wearing proof that 50,000 degrees of heat once passed through that exact piece of sand. But fulgurites are just one way lightning marks the earth. The bolts themselves take many forms, appear in many guises, some common, some rare, all beautiful. Most lightning never touches the ground. About 3/4 of all lightning bolts stay entirely in the clouds, jumping from one part of a storm to another. Cloud-to-cloud lightning. We rarely think about it because it does not strike things we care about. But it happens constantly, more often than the ground strikes we pay attention to. These bolts travel horizontally through the cloud or from cloud to cloud when storms are close together. They follow the same physics as ground strikes. Stepped leader, return stroke, all of it, just aimed sideways instead of down. They light up the clouds from inside, and what we see from below is the glow filtering through water and ice. This creates sheet lightning, not a bolt, not a fork, just a soft flash that illuminates part of the sky. The actual lightning channel is hidden behind the cloud. We see only the diffused light spread across a wide area, gentle and almost peaceful compared to the violent crack of a close ground strike. Sometimes wind moves the lightning channel while it flickers. This creates ribbon lightning. The bolt stays in roughly the same place, but strong wind pushes each successive stroke slightly to the side. Your eye sees multiple parallel channels because the wind moved the visible path between strokes. It looks like a ribbon or a curtain, multiple bright lines hanging in the sky instead of a single bolt. Bead lightning is stranger. As a lightning channel fades, sometimes it breaks up into segments. The bright line fragments into a series of glowing dots, like pearls on a string. This lasts only a fraction of a second. Scientists think it happens when some parts of the channel cool faster than others, creating bright spots separated by darker gaps. Or possibly the channel fragments due to instabilities in the plasma. Either way, it appears rarely, and most people who see it assume they imagined it because it vanishes so quickly. Then there is ball lightning. This is where things get genuinely mysterious. Ball lightning appears as a glowing sphere, usually about the size of a basketball, floating through the air after a lightning strike. It drifts slowly. Sometimes it passes through walls. Sometimes it explodes. Sometimes it just fades away. Reports describe it in many colors, most often orange or yellow, occasionally blue or white. The problem is that ball lightning is barely understood. Scientists debate whether it even exists as a distinct phenomenon, or if people are seeing something else. There are reports going back centuries, thousands of eyewitness accounts, but almost no physical evidence, no clear photographs, no measurements taken during an event. Theories abound. Maybe it is a plasma ball held together by electromagnetic fields. Maybe it is burning silicon nanoparticles, created when lightning vaporizes soil. Maybe it is an optical illusion, after images burned into the eye by bright lightning. Maybe it involves quantum effects we do not fully understand yet. Nobody knows for certain. What makes ball lightning so difficult to study is that it appears randomly and lasts only seconds. You cannot predict where or when it will happen. You cannot create it reliably in a lab, though people have tried. Some experiments have produced glowing spheres, but whether these match natural ball lightning remains unclear. Yet the reports persist. Pilots see it. Sailors see it. People see it in their homes after close lightning strikes. The consistency of descriptions across cultures and centuries suggests something real is happening, even if we cannot explain it yet. But lightning reaches beyond even these strange forms. It extends upward from storms into the upper atmosphere, creating displays so rare that scientists only discovered them in recent decades. That is where we go next, to the lightning that shoots towards space. Above the clouds, in the thin air of the upper atmosphere, lightning creates shapes that look like something from science fiction. Red jellyfish, blue columns, expanding rings of light. These phenomena were unknown until the 1980s because you cannot see them from ground level. You have to be above the storm, looking down, or far away, looking horizontally across hundreds of miles. Pilots occasionally reported strange lights above thunderstorms, but scientists dismissed these reports for decades. Then, in 1989, a camera accidentally captured one during a rocket test. The image showed a massive red glow above a storm, reaching up towards space. Scientists realized the pilots had been right all along. These are called sprites. They look like red jellyfish or carrots hanging upside down in the mesosphere, 50 to 60 miles above Earth's surface. That is higher than weather balloons fly, higher than most meteors burn up. Sprites exist in the edge of space. A sprite forms after a powerful positive lightning strike hits the ground. The sudden change in electrical field between the cloud and ground propagates upward through the atmosphere at nearly the speed of light. When this wave reaches the mesosphere, where air is thin and easy to ionize, it creates a brief electrical discharge. The discharge glows red because it excites nitrogen molecules in the thin air. Sprites last only a few milliseconds. Blink and you miss them. They appear in clusters, sometimes dozens at once, spreading across 100 miles of sky. The tendrils reach downward toward the storm, sometimes extending 20 miles vertically. All of this happening in silence, because there is not enough air that high up to carry sound. Blue jets are different. They shoot upward from the tops of thunderstorms like fountains. narrow cones of blue light traveling at about 200 miles per second, reaching altitudes of 25 to 30 miles. They do not need a ground strike to form. They emerge directly from particularly active storm cells. The blue color comes from neutral and ionized molecular nitrogen. Lower atmosphere means more nitrogen molecules to excite. The jets last longer than sprites, sometimes persisting for a few tenths of a second. Still brief by human perception, but long enough that high-speed cameras can capture their full evolution from emission to fade. Then there are ELVs. The name stands for emissions of light and very low frequency perturbations, due to electromagnetic pulse sources, but everyone just calls them ELVs. They appear as expanding rings of light, like ripples on a pond made of luminescence, spreading across the bottom of the ionosphere. ELVs happen when electromagnetic pulses from lightning propagate upward and ionize the thin air about 60 miles up. The ring expands outward at the speed of light, reaching diameters of 300 miles or more. They last less than a millisecond. The briefest of all upper atmosphere phenomena. Most ELVs are detected by specialized cameras because they happen too fast for human eyes to register. All of these phenomena were invisible to science until recently because you need the right vantage point. Storm chasers started capturing sprites using special cameras in the 1990s. The International Space Station has filmed them from orbit. Pilots now know to watch for them above severe storms. They happen constantly. Every major thunderstorm probably produces sprites and jets and ELVs, but most go unobserved because few people are in position to see them. These are not rare events, just rarely witnessed. What this tells us is that lightning couples the troposphere to the ionosphere. It creates electrical connections between the weather layer and the edge of space. The atmosphere is not separate layers existing independently. It is one integrated system, with lightning serving as the wire connecting ground to space. Lightning does not just create light and heat, it broadcasts. Every bolt is a radio transmitter, sending signals across the entire electromagnetic spectrum, from ultra-low frequencies that can travel around the world to ultra-high frequencies that bounce off the ionosphere. Lightning speaks in every language of electromagnetic radiation. The bolt itself is an antenna, a temporary antenna miles long, carrying thousands of amperes of current, switching on and off in milliseconds. When electric current changes rapidly, it creates radio waves. This is basic physics. The same principle makes your radio work, makes your phone transmit. Lightning just does it at extreme scale with extreme power. The strongest emissions happen at very low frequencies, below 30 kHz. These waves travel far because Earth's surface and the ionosphere form a waveguide, a natural channel that contains and directs the waves. A lightning strike in Africa can be detected by radio receivers in Antarctica. The waves circle the planet, bouncing between ground and ionosphere, potentially making multiple trips around Earth before fading. This is why AM radios crackle during thunderstorms. You are hearing lightning. Each burst of static is a bolt somewhere within a few hundred miles, its radio emissions picked up by your antenna. The closer the storm, the louder the static. FM radio is less affected because it operates at higher frequencies that do not travel as far through the atmosphere. Scientists use this to track storms. Networks of radio receivers detect lightning strikes and calculate where they came from, based on the timing differences between stations. If 3 stations detect the same strike you can triangulate its location precisely. This creates real-time lightning maps showing every bolt striking anywhere in a region. Lightning also creates something called radioatmospherics, or spherics. These are short bursts of radio energy at multiple frequencies. A single bolt produces spherics across a wide band, from a few kilohertz up to several megahertz. Each frequency travels differently through the atmosphere, so the received signal stretches out, creating a characteristic whistle shape if you convert it to audio. Some lightning emissions reach much higher frequencies, up in the very high frequency range, above 30 megahertz. These waves do not follow Earth's surface. They shoot straight up, reflect off the ionosphere, and come back down hundreds of miles away. Ham radio operators sometimes hear lightning from distant storms bouncing off the ionosphere, sounding like sharp clicks on their receivers. The electromagnetic pulse from a close lightning strike can damage electronics. The sudden change in magnetic field induces currents in wires, circuit boards, anything conductive. This is why lightning protection systems include surge protectors, not just to handle direct strikes, but to absorb the electromagnetic pulse that radiates outward from any nearby bolt. Research satellites detect lightning from space by monitoring these radio emissions. Sensors in orbit pick up the very low frequency waves that propagate up through the ionosphere. This lets scientists map global lightning activity, see patterns across continents and oceans, understand how storm frequency changes with seasons and climate. Some of these radio emissions interact with the Earth's magnetic field in complex ways. They can trigger waves in the plasma that fill space near Earth, creating effects that ripple through the magnetosphere. A lightning bolt in Brazil can influence charged particles trapped in the Van Allen radiation belts, thousands of miles above the planet. Lightning also produces optical emissions beyond visible light. Ultraviolet radiation, X-rays. Some powerful bolts even create gamma rays, the most energetic form of electromagnetic radiation. These are absorbed by the atmosphere quickly, but satellites have detected them bursting upward from thunderstorms. Every frequency tells us something. The very low frequencies reveal the bolt's total current. Higher frequencies indicate how quickly the current changed. X-rays suggest the formation of very high energy electrons. Lightning is not just one event. It is a cascade of processes, each creating its own signature in the electromagnetic spectrum. And all of this energy radiates outward, traveling through Earth itself, spreading through the ground beneath our feet. When lightning strikes ground, the energy does not just stop. It spreads, radiates outward through soil and rock in every direction, seeking paths of least resistance, flowing away from the strike point like water soaking into dry earth. This is called ground current. It is electricity traveling horizontally through the ground instead of vertically through air. And it is dangerous, more dangerous than the lightning bolt itself for anyone standing nearby. Most lightning injuries come from ground current, not direct strikes. Here is why. When a bolt hits the ground, it injects millions of volts into a small area. That energy has to go somewhere. It spreads outward, but voltage drops with distance. Right at the strike point, the ground might be at 1,000,000 volts. 10 feet away, maybe half that. 20 feet away, lower still. This creates a voltage gradient, a slope of electrical potential, radiating from the strike. If you are standing with your feet apart during a nearby strike, one foot might be on ground at higher voltage than the other. This difference makes current flow through your body, up one leg and down the other. This is step potential. Your stride becomes a conductor. The wider your stance, the more voltage difference between your feet, the more current flows. Cows die from this frequently during thunderstorms. Their legs are farther apart than human legs. A strike nearby can create enough step potential to drive fatal current through their body from front legs to back legs. You sometimes see multiple cows dead in a field after a storm, all from ground current from a single bolt that did not directly hit any of them. Earth conducts electricity, but not well. Soil has high resistance compared to metal wires. This means the current creates heat as it flows. The ground around a strike point actually warms slightly from the energy dissipating through it. In wet soil, the moisture heats up. In very dry or sandy soil, sometimes the heat is intense enough to fuse sand into fulgurite underground, where the main current traveled. The current follows moisture. Wet soil conducts better than dry soil. Tree roots conduct well because they contain water. Underground water pipes and cables provide excellent paths. The electricity flows preferentially through these conductive routes, creating a complex three-dimensional pattern of current spreading outward and downward from the strike point. This is why lightning often hits the same spots repeatedly. A tall tree attracts strikes because it is the highest object, but also because its deep roots provide a good ground connection. Once lightning has struck there, the path is established. The soil has been ionized slightly. The tree's root system has proven itself as a conductor. Future storms find that same tree because it remains the path of least resistance. Buildings with lightning rods use this principle. The rod provides an attractive target, and thick copper cables route the current safely into the ground through metal stakes driven deep into earth. The current still spreads, still creates ground current, but away from the building where people are not standing. The spread distance depends on soil type. In rocky terrain with poor conductivity, ground current might only reach dangerous levels within 30 feet of a strike. In wet clay soil with good conductivity, step potential can be hazardous 100 feet away. There is no simple rule. Every strike behaves differently based on local conditions. Lightning energy can travel surprising distances underground. Current from a strike has been detected in basement wiring half a mile away from the bolt. It found a path through underground utilities, through mineral veins in rock, through any conductive material connecting the strike point to distant locations. Eventually, the energy dissipates completely, converts to heat in the soil, spreads so wide that the current density drops to nothing. The earth absorbs it, and the voltage returns to normal. But for those few seconds after the strike, the ground itself is electrically alive, dangerous, conducting the power of the sky through the planet beneath your feet. Some places collect these strikes more than others, concentrate lightning like magnets. There is a place on Earth where lightning strikes nearly every night. A lake in Venezuela, surrounded by mountains, where storms form with clockwork regularity. Lake Maracaibo, the lightning capital of the world. The lake experiences lightning about 300 nights per year, not scattered strikes, concentrated storms that produce thousands of bolts per hour. The phenomenon is so consistent that sailors used it for navigation centuries ago. They called it the Maracaibo Beacon, a permanent lighthouse made of lightning. Why there? Geography creates a perfect recipe. The lake sits in a basin surrounded by the Andes Mountains. During the day, the sun heats the water. Warm, moist air rises. At night, cool mountain winds flow down the slopes. The warm air from the lake collides with cool mountain air. This collision happens right over the lake, every night. The result is constant thunderstorm formation. The storms build in the same location repeatedly because the geography does not change. The mountains stay put. The lake keeps evaporating. The temperature difference between day and night remains consistent. So the lightning returns, night after night, year after year. Locals barely notice it anymore. It is just part of the environment. But Lake Maracaibo is not the only hotspot. Central Africa has several. The Congo Basin experiences tremendous lightning activity because of similar geographic factors. Mountains surrounding lowlands, large bodies of water creating moisture, temperature differentials between day and night. The recipe repeats. Florida holds the record for lightning in the United States. The Florida Peninsula juts out into warm ocean water. Sea breezes from both coasts converge in the middle. Warm, moist air rises rapidly in the afternoon heat. Thunderstorms form almost daily in summer. The state averages more than 1 million lightning strikes per year. The pattern is clear. Lightning concentrates where conditions favor thunderstorm development. You need moisture. You need heat. You need something to make warm air rise quickly. Mountains help. Large bodies of water help. Tropical locations help, because they have both heat and moisture in abundance. Globally, lightning peaks in the tropics. The equatorial regions experience about 70% of all lightning strikes worldwide. This makes sense. The sun heats tropical regions most intensely. More heat means more convection, more storms, more lightning. As you move toward the poles, lightning becomes rarer because there is less solar heating to drive storm development. Seasons matter too. In the northern hemisphere, lightning peaks in summer when land heats up and creates strong convection. Winter, lightning is rare, though it happens occasionally in strong coastal storms. In the southern hemisphere, the pattern reverses. Their summer, our winter, brings peak lightning to places like Argentina and Australia. Ocean lightning is less common than land lightning. Water does not heat up as quickly as soil and rock. This means weaker convection over open ocean. Most oceanic lightning happens near coasts or over warm currents like the Gulf Stream, where temperature contrasts still exist. The middle of the Pacific sees relatively little lightning compared to continental regions. Mountains create interesting patterns. Lightning often concentrates at specific elevations where conditions align. In the Himalayas, certain valleys experience frequent strikes because they channel moisture and create local circulation patterns. The Rocky Mountains in North America show similar hotspots. Cities can influence lightning too. Urban heat islands, areas where cities are warmer than surrounding countryside, can trigger or enhance thunderstorms. The extra heat creates updrafts. Pollution particles provide nuclei for water droplets to form around. Some studies suggest cities slightly increase local lightning frequency, though the effect is subtle compared to natural geographic factors. All of these patterns feed into a larger system. Lightning is not random. It follows rules, responds to geography, concentrates where conditions favor electrical storm development. And humans learned to work with these patterns, to understand lightning well enough to eventually harness its power. For most of human history, lightning was mysterious. People knew it was dangerous. They knew it started fires and killed people. But they did not know what it actually was. Some thought it was divine anger. Others believed it was burning gases in the clouds. Nobody had the framework to understand it as electricity. Then, in 1752, Benjamin Franklin flew a kite in a thunderstorm. This is the famous story. A key attached to the string, his hand near the key. When lightning flashed nearby, sparks jumped from the key to his hand. Small sparks, nothing like the massive bolt in the clouds, but enough to prove his hypothesis. Lightning was electricity. This was revolutionary. People know about static electricity. You could rub amber with cloth and pick up small objects. You could get shocked touching a doorknob. But these were tiny effects, party tricks. Lightning was powerful, deadly, capable of splitting trees and burning buildings. Franklin connected them. Same phenomenon, different scale. He proved it with careful experiments. He charged a Leyden jar, an early capacitor, using the electricity collected from his kite. Then he demonstrated that this captured electricity behaved identically to electricity generated by friction machines. It created sparks. It could be stored and discharged. It followed the same rules. Lightning was electrical discharge. Nothing more mysterious than that. This changed everything. If lightning was electricity, then it could be studied. It could be measured. Most importantly, it could be controlled. Franklin immediately invented the lightning rod, a pointed metal rod attached to the top of a building, connected by wire to a metal stake driven into the ground. Simple, elegant, effective. The rod attracts lightning because it is the highest point, and its sharp tip concentrates electrical charge. When lightning strikes, the current flows through the wire into the ground instead of through the building. No fire, no damage, just a safe path for the energy to dissipate into Earth. People were skeptical. Some religious leaders objected, claiming it was presumptuous to interfere with divine will. But Franklin's rods worked. Buildings with lightning rods survived storms that destroyed nearby unprotected structures. The evidence was undeniable. Within decades, lightning rods appeared on churches, government buildings, ships' masts. This began the scientific study of lightning. Researchers started measuring it, cataloguing different types, investigating how it formed. They discovered positive and negative charge. They learned about ionization of air. They mapped the electrical fields in thunderstorms, using instruments lifted by kites and balloons. The understanding grew slowly. It took another 100 years to figure out the stepped leader and return stroke. Another century to discover sprites and jets. Even now, we are still learning. But Franklin started it. He took a phenomenon considered supernatural and brought it into the realm of physics. His insight was recognizing similarity across scales. He saw that the tiny spark from rubbing amber was fundamentally the same as the massive bolt splitting the sky. The only difference was magnitude. This kind of thinking, finding unity in apparently different phenomena, drives all of science. The lightning rod itself saved countless lives. Before its invention, lightning fires regularly destroyed entire city blocks. Churches, with their tall steeples, burned frequently. Gunpowder magazines exploded when lightning struck. Ships sank after lightning shattered their masts. The rod reduced all of this. A simple metal spike changed the relationship between humans and lightning, from helpless terror to manageable risk, and this was just the beginning. Understanding lightning as electricity opened doors. It led to generators, motors, power grids, all the electrical technology we depend on today. Franklin's kite experiment connects directly to the lights in your room, the device you are listening on. Everything electrical traces back to that moment of recognition that lightning and electricity were the same. Franklin gave us the lightning rod. We took that basic idea and built an entire industry around protecting everything, from homes to spacecraft from electrical storms. Modern lightning protection is more sophisticated than a rod and a wire. Buildings use air terminals, multiple metal points placed strategically across the roof. Not just one rod at the highest point, but a network. The terminals connect to thick copper or aluminum cables called down conductors. These run down the outside of the building, sometimes hidden inside walls, and terminate in ground rods driven 10 feet or more into earth. The system creates a cone of protection. Each air terminal protects an area roughly 45 degrees from its tip. For a rod 10 feet tall, this means a circle about 20 feet across. Large buildings need dozens of terminals to cover the entire roof. The placement matters. Every part of the structure needs to be within a protected zone. But the rod itself is only part of the solution. The real danger for modern buildings comes from surges. When lightning strikes nearby, even if it hits a lightning rod perfectly, the electromagnetic pulse induces voltage spikes in electrical wiring. These spikes can destroy computers, televisions, appliances, any sensitive electronics. Surge protectors defend against this. They sit between the power source and your devices. Inside is a component called a metal oxide varistor. At normal voltages, it does nothing. But when voltage spikes above a threshold, the varistor suddenly conducts, diverting the surge to ground before it reaches your equipment. The whole process happens in nanoseconds. Home surge protectors handle small spikes, but buildings need industrial versions at the main electrical panel. These can absorb massive surges, hundreds of thousands of amps briefly. They sacrifice themselves to protect everything downstream. After a major surge, they need replacement, but they saved everything else. Telecommunications equipment needs protection too. Phone lines, internet cables, anything that enters a building from outside can carry induced currents during a lightning strike. Special surge protectors exist for each type of connection. Data centers use multiple layers of protection because a single surge could destroy servers worth millions. Aircraft face unique challenges. They cannot ground to earth while flying. Instead, they use static discharge wicks, small metal rods on wingtips and tail edges. Lightning typically enters the aircraft at one extremity and exits at another. The wicks provide preferred exit points. The fuselage, being metal, conducts the current around the passengers inside. It is a Faraday cage. The people remain safe because the electricity flows through the skin of the aircraft, not through the interior. We learned these techniques by studying what fails. Every lightning accident teaches something. Tower collapses showed us we needed better bonding between metal components. Electronics failures led to better surge protection. Fires in protected buildings revealed that having a lightning rod is not enough if the grounding is inadequate. Wind turbines present new problems. Tall structures in open areas, often on hilltops. They attract lightning constantly. A single turbine might be struck dozens of times per year. Engineers install extensive protection systems in the blades, down the tower, throughout the electrical systems. Even so, lightning damage remains a significant maintenance cost for wind farms. The same principles protect communication towers, power transmission lines, even the launch pads at rocket facilities. Anywhere humans build tall structures, lightning protection follows. The technology has become routine, invisible, built into every major construction project. Power grids are particularly vulnerable. High voltage transmission lines stretch for miles through open country. Tall pylons, making perfect lightning targets. Each tower has grounding systems, but a direct strike to the line itself can cause blackouts affecting thousands of people. Utilities use lightning arresters, devices that detect overvoltage and shunt it to ground before it can damage transformers or other equipment. Yet, despite all this protection, lightning still surprises us, still finds ways through our defenses, still poses questions we cannot fully answer. We know a lot about lightning, but we do not know everything. Some fundamental questions remain unanswered despite decades of research. The most basic one: how does lightning actually start? We understand the charge separation, ice particles colliding, building up voltage differences. We understand the breakdown threshold, the point where air stops insulating and starts conducting. But the math does not work. The electric field in thunderclouds, as measured by instruments, is not quite strong enough to trigger breakdown. Not according to classical physics. Air should start conducting at about 3 million volts per meter. Measurements show thundercloud fields reaching only about 100,000 volts per meter, maybe 300,000 in the most intense storms. That is 10 times too weak. Yet lightning happens anyway. Something is missing from our understanding. One theory involves cosmic rays. These are high-energy particles from space, mostly protons, constantly bombarding Earth's atmosphere. When a cosmic ray hits air molecules, it creates a cascade of secondary particles. This ionization might provide the initial conducting path that lets lightning form at lower field strengths than pure theory predicts. The idea is that cosmic rays create small conductive channels through the air. When the electric field in a cloud reaches a certain threshold, these pre-ionized channels let electricity start flowing more easily. The lightning uses these cosmic ray tracks as starter paths. Evidence supports this. Lightning initiation correlates with cosmic ray detection, but it is not proven conclusively. Ball lightning remains unexplained. Thousands of reports, consistent descriptions across centuries, yet no accepted physical theory accounts for it. How does a sphere of plasma maintain itself in open air for seconds or even minutes? Plasma wants to expand, dissipate, cool. What contains it? What powers it? Some researchers think ball lightning is a chemical phenomenon. Maybe lightning vaporizes silicon from soil, creating a cloud of nanoparticles that burn slowly. Others suggest it involves quantum effects or exotic states of matter. A few think it might be an optical illusion, electrical activity in the eye itself, caused by electromagnetic pulses. Nobody knows for certain. Then there is antimatter. In 2009, satellites detected positrons, the antimatter equivalent of electrons, being produced by thunderstorms. Positrons annihilate when they contact normal matter, creating gamma rays. Lightning somehow generates antimatter. This was completely unexpected. We are still figuring out how and why it happens. The leading explanation involves gamma rays created by high-energy electrons in lightning channels. These gamma rays can convert into electron-positron pairs near atomic nuclei. The positrons quickly annihilate, but their brief existence means lightning is creating antimatter routinely. Every major storm might be producing small amounts of antimatter that immediately destroys itself. We also do not fully understand the relationship between lightning and climate. Does lightning frequency increase with global temperature? Some models predict more lightning as the planet warms, because warmer air holds more moisture and creates stronger convection. But the data is messy. Measuring global lightning accurately only became possible with satellites in recent decades. We do not have long-term records for comparison. Lightning might influence atmospheric chemistry more than we realize. Every bolt creates nitrogen oxides, but also contributes to ozone formation and destruction in complex ways. The net effect on climate is still being calculated. Lightning might be a significant but overlooked factor in atmospheric balance. High-altitude lightning, the sprites and jets and elves, were only discovered in the last few decades. We are still cataloguing them, still learning what conditions produce what phenomena. There might be other types we have not observed yet, other electrical effects in the upper atmosphere waiting to be discovered. The frontier of lightning science is wide open. Every question answered reveals new questions. Every measurement finds unexpected complexity. Right now, somewhere on Earth, about 2,000 thunderstorms are happening. 2,000. At any given moment. They are not random. They are connected. All of them participate in a single planetary system called the global electric circuit. Here is how it works. The atmosphere has a voltage. The ionosphere, 60 miles up, sits at about 300,000 volts, relative to Earth's surface. That voltage difference exists constantly. You are standing at the bottom of a 300,000 volt battery that extends from the ground beneath your feet to the edge of space above your head. This should drain away. Voltage differences want to equalize. Current should flow from the ionosphere down to Earth until the difference disappears. And current does flow. About 1,000 amperes, constantly traveling downward through the entire atmosphere. This is called fair weather current because it happens even when the sky is clear. If only fair weather current existed, the atmospheric voltage would drain to zero in about 15 minutes. The battery would die, but it does not. The voltage remains steady. Something constantly recharges it. That something is lightning. Every thunderstorm is a generator. The charge separation we talked about earlier. Ice particles in clouds creating voltage differences. That process pumps electricity upward. Lightning carries negative charge from ground to cloud. Then, cloud-to-cloud discharges move it higher. Eventually, the charge reaches the ionosphere. The storms act as cables connecting Earth's surface to the ionosphere. They are the power supply maintaining the atmospheric voltage. 2,000 storms, all of them working simultaneously, all of them pumping about 1 ampere upward on average. 2,000 amperes going up through storms. 1,000 amperes coming down through fair weather. The difference maintains the global voltage. This means every storm is electrically connected to every other storm through the ionosphere. A lightning bolt in Brazil contributes to the atmospheric voltage over Australia. The circuit is truly global. The ionosphere conducts well enough that charge spreads around the world in minutes. Scientists can measure this. The fair weather current changes with time of day based on where thunderstorms are most active. When Africa has peak storm activity, the global voltage increases slightly. When South America's storms ramp up, it increases more. The system breathes with the rhythm of global convection. The atmospheric voltage affects everything beneath it. A small current flows through your body right now, about 1 picoampere, as you conduct some of that fair weather current to ground. Trees conduct more because they are taller. Mountains conduct more still. Everything participates in this global flow, usually too weak to notice, but always present. This circuit influences atmospheric chemistry. The electric field affects how particles clump together, how water droplets form, potentially how clouds develop. Some researchers think changes in the global circuit might correlate with climate variations, though this remains controversial. Lightning is essential to maintaining the circuit. Without thunderstorms constantly recharging the atmosphere, the voltage would collapse. The global electric circuit would cease to exist. This has been true for billions of years, since Earth first had an atmosphere thick enough to support storms. Lightning has been charging the sky since before life existed, maintaining this planetary battery through geological ages. The circuit is remarkably stable, despite storms forming and dissipating, despite day and night, despite seasons. The atmospheric voltage stays within a narrow range. The system self-regulates. If storms become less frequent, the voltage starts to drop. But lower voltage means stronger fair weather electric fields, which might influence cloud formation, potentially creating more storms. The feedback mechanisms keep everything balanced. The circuit connects everything. Every storm, every bolt, every fair weather day, all part of one system, one electrical structure wrapping the entire planet, powered by the endless cycle of water and heat and ice particles colliding in the dark. And this system has been running for an almost unimaginable span of time. 4 billion years ago, Earth had lightning. The planet was young, hostile, nothing like today. The atmosphere was thick with methane, ammonia, carbon dioxide, water vapor. No oxygen, no life. But there were storms, and where there are storms with moisture and convection, there is lightning. Those early bolts were probably more frequent than today's. The atmosphere was denser, more turbulent. Volcanic eruptions pumped ash into the air constantly, providing nuclei for water droplets and ice crystals. The temperature swings between day and night were more extreme. All of this created ideal conditions for electrical storms. We talked about the Miller experiment in an earlier chapter. Lightning creating amino acids from simple atmospheric gases. That probably happened countless times on early Earth. Every bolt that struck near water, every discharge through the primitive atmosphere, contributed molecules to the primordial soup. Not much per strike, but billions of strikes over millions of years add up. Some scientists think lightning played a direct role in life's origin, not just creating building blocks, but providing the energy to assemble them into more complex structures. Lightning's energy could forge chemical bonds that would not form otherwise. It could concentrate molecules in certain locations. It could create temperature and pressure conditions where chemistry happens faster. There is evidence in the rocks. Ancient fulgurites, billions of years old, preserved in geological formations. These prove lightning struck back then. The glass tubes contain traces of the atmosphere they formed in, snapshots of ancient air composition frozen in stone. As Earth changed, lightning changed with it. When photosynthetic organisms started producing oxygen about 2.5 billion years ago, the atmosphere slowly transformed. Lightning began creating nitrogen oxides more efficiently because oxygen was present to combine with the split nitrogen atoms. This increased nitrogen fixation, which fed more plant life, which produced more oxygen. A feedback loop where lightning participated in terraforming Earth. Through all of Earth's major changes, lightning continued. During ice ages, when glaciers covered continents, lightning still struck, though probably less frequently in the frozen regions. During warm periods, when tropical forests spread to the poles, lightning increased. Every climate shift, every geological era, lightning adapted to the conditions, but never stopped. The dinosaurs lived beneath lightning. Every storm in the Mesozoic era produced bolts essentially identical to modern ones. The same physics, the same charge separation, the same brilliant return stroke heating air to 50,000 degrees. A Tyrannosaurus could have been killed by ground current, just like a modern cow, following the same rules of step potential. Early humans knew lightning intimately. They saw it start wildfires. They probably learned to use those fires before they learned to make fire themselves. Lightning provided light, warmth, and cooked food indirectly. Some anthropologists think the control of fire, fundamental to human development, began with lightning-started blazes that our ancestors learned to maintain and transport. Ancient cultures across the world associated lightning with gods. Zeus, Thor, Indra, Raijin, dozens of thunder deities, all reflecting the awe and terror lightning inspired. These myths were not just superstition. They were attempts to understand and respect a powerful force that clearly influenced human life. The oldest written records mention lightning. Babylonian tablets describe storms and their effects on crops. Egyptian hieroglyphs show lightning, bolts striking the earth. Chinese oracle bones record divinations based on thunder patterns. Lightning has been part of human consciousness as long as we have had consciousness to record. And through all of this deep time, through geological ages and evolutionary epochs and human history, each lightning bolt was unique. Every single one followed the same laws but expressed them differently. No two lightning bolts are exactly the same. Not in 4 billion years of Earth's history. Not among the billions of strikes happening each year. Every bolt is unique. Every path is different. This is not randomness. It is mathematics expressing itself through electricity. The branching pattern is fractal. This means it repeats similar shapes at different scales. A main channel splits into smaller branches. Those branches split into even smaller ones. The pattern continues down to microscopic levels. Zoom in on any branch, and you see the same branching structure repeated. This is nature's signature, the same pattern that appears in trees, rivers, blood vessels, lungs. Why does lightning branch? Because it is searching for the easiest path. Air is not uniform. Some regions have slightly more moisture. Others have more ions left over from previous lightning or cosmic rays. Some areas are warmer or cooler. The stepped leader probes all these variations simultaneously. Each branch is testing a different route. Most branches fail. They reach a point where the resistance is too high and stop extending. But one branch finds the best path and becomes the main channel. The others remain visible as dimmer side channels. This creates the characteristic forked appearance we recognize as lightning. The angles of branching follow probabilities rather than fixed rules. A branch might split at 30 degrees or 60 degrees or 90 degrees. It depends on local conditions at that exact moment in that specific volume of air. The mathematics is deterministic, following physics precisely, but the initial conditions are so complex that the result appears random. Scientists use fractal mathematics to model lightning. Fractals describe systems where small changes in starting conditions create large differences in outcomes. Lightning fits this perfectly. Change the position of a few water droplets in a cloud and the lightning path shifts. Change the temperature by a degree and new branches form in different locations. The beauty of fractal patterns is that they are efficient. Trees branch to expose maximum leaf area to sunlight using minimum trunk material. Rivers branch to drain watersheds most effectively. Lightning branches to ionize the largest volume of air using the least energy. The fractal structure is not decoration, it is optimization. Each bolt records information about the atmosphere it passed through. A bolt with many branches suggests highly variable air, lots of turbulence, complex moisture patterns. A bolt with few branches indicates more uniform conditions. The spacing between branches tells you about the size of the air masses involved. The angles reveal wind patterns. You could, in theory, reconstruct the atmospheric conditions from a detailed photograph of a lightning bolt. Not completely, but partially. The lightning preserves a record of what the air was like in that moment. A snapshot frozen in the geometry of the discharge. Some lightning appears straight. These bolts found uniform air all the way down. Same conductivity throughout. Rare, but it happens. Most lightning zigzags because air changes constantly. Temperature varies. Humidity fluctuates. Pressure shifts. The lightning follows these variations precisely, creating a path that maps the invisible structure of the atmosphere. The branching also increases the surface area of the discharge. More branches mean more air gets heated, more nitrogen gets fixed, more chemical reactions occur. The fractal geometry maximizes the lightning's impact on its environment. Mathematicians study lightning patterns to understand natural fractals. Engineers use lightning geometry to design better antennas and electrical systems. Artists appreciate the beauty of the forms. The same bolt can be analyzed scientifically, replicated mathematically, and admired aesthetically. It is data and art simultaneously. And yet, for all this complexity, all this uniqueness, all these billions of different paths through 4 billion years, every bolt shares the same fundamental purpose: connecting Earth to sky, completing the circuit, maintaining the balance between ground and cloud, each one unique in its details, but identical in its function. This brings us back to where we began, to the simple wonder of light in the sky. We began with a simple fact. Lightning strikes Earth 50 times every second. 50 brilliant connections between sky and ground, happening right now as you listen, as you breathe, as you settle deeper into rest. You understand more now. You know that lightning is not just a flash in the distance. It is ice particles colliding in darkness. It is a stepped leader feeling its way down. It is a return stroke blazing upward at a third the speed of light. It is nitrogen being fixed into soil. It is ozone being born. It is the global electric circuit maintaining the voltage between ground and space. It is chemistry and physics and mathematics all at once. It is ancient as the planet and new with every bolt. It is understood in its fundamentals and mysterious in its details. It is dangerous and essential. It is feared and beautiful. But mostly, it is a bridge. Lightning connects earth to sky, connects cloud to ground, connects the weather layer where we live to the edge of space 60 miles up. It ties the global electric circuit together, makes every storm part of one planetary system. It links ancient Earth to modern Earth through 4 billion years of continuous strikes. It connects simple molecules to complex ones, potentially sparking the chemistry that led to life. And it connects us to wonder, to that childlike sense of awe at nature's power. Standing beneath a thunderstorm, watching light write temporary messages across the sky, you are witnessing the same phenomenon that has played out since before life existed. The same physics, the same beauty, the same immense energy rendered briefly visible. You are small beneath these lights. The voltage in a single bolt could power your home for months. The heat in the channel is 5 times hotter than the sun's surface. The sound can hurt if you are close enough. Lightning operates at scales that dwarf human experience. Yet, you are also part of it. Your body creates its own tiny electricity with every thought, every heartbeat. The same electrons flowing through your nerves are flowing through lightning channels. You and lightning share the same fundamental particles, follow the same laws of physics. You are made of the same universe that makes lightning. The connection is literal. There is peace in this understanding. Lightning is not random chaos. It is pattern following rules. It is fractals and circuits and chemistry. It is knowable, not fully known, perhaps never fully known, but knowable. Each bolt carries information. Each strike adds another data point to our understanding. Tonight, storms are forming somewhere. Ice particles are colliding. Charge is separating. Stepped leaders are descending invisibly. Return strokes are blazing upward. Thunder is rolling across valleys and plains. Nitrogen is being fixed. Ozone is forming. The global circuit is being maintained. All of it happening whether you watch or not. All of it continuing as you close your eyes. If these quiet journeys through science bring you calm, consider subscribing. You will join others who find peace in understanding the world around us. And if you enjoyed exploring lightning tonight, leave a comment. Tell us what surprised you most. Tell us where you are, what time it is there, what you see when you look up at your own sky. The universe is vast and complex and sometimes frightening, but it follows rules. It can be understood, and there is comfort in that knowledge. Rest now. Let the facts settle. Let the wonder remain. The lightning will continue its dance above you, connecting earth to sky, maintaining the circuit, writing its temporary poetry in light and thunder. Sleep well beneath these lights.